So firstly, I'm going to run through just a bit of an overview of how we approach hardware and embedded system security testing here at CCX. Talk about some of our sort of past research in the space. Give you a bit of a sneak peek into a presentation I'll be doing later in the year around hardware hacking, and then we'll open up the floor for a bit of a Q&A. So firstly, who am I? As Michael said, I've been leading out the hardware and embedded system security testing side of things for a few years. What got me interested in hardware hacking? In my previous job with the New Zealand Police, I often had to pull off flash chips from dead or very broken phones. These are often eMMC chips, and so I kind of enjoyed that hands-on hardware electronic stuff. I joined Insomnia, now CyberCX, 5 years ago, doing just normal pen tester stuff, web app, mobile app testing, things like that. But in that time, I did quite a few router sort of consumer device security tests, and to me that was really a bit of a gateway drug. Like, I really enjoyed that hands-on device hacking. And for context, I'm really quite a noob when it comes to electronic stuff. There are people within CyberCX that are much more experienced in that space, but I definitely really enjoy the sort of hands-on device hacking. I've done a few presentations over the last few years around hardware hacking, mostly in consumer products, so my old DJ controller, some home routers, the PlayStation Classic, which was a kind of hobbyist game console. Also, I used to run in-person meetups for people interested in hardware hacking in Wellington, but as you can imagine, COVID and whatnot has sort of made that quite difficult. But there was definitely a decent group of people that really enjoyed hacking devices, and we had some great presentations and hands-on hacking. And yeah, if you want to get in touch with me, either email or LinkedIn is good. So here in New Zealand, we have two hardware lab spaces, one in Wellington, one in Auckland. These spaces have been built up by me and Gavin in Auckland, who's one of our principal consultants. Gavin and I have a good relationship where we essentially just buy two of everything. So both of these spaces are almost identical. And really, these photos don't do these spaces great justice. We've got so many boards, connectors, little bits and bobs, but it gives you a bit of a feel for what we have, microscope, oscilloscope, soldering equipment and whatnot. And really, my goal with these spaces is just to have as much equipment as possible to do all those weird edge case things with hardware. Also, for CyberCX Wellington, we'll be moving into a new office at some stage. That's going to have a bit more of a purposeful built hardware space, a closable door, for example, and some better extraction for toxic fumes from soldering and other sort of mischief we might get up to. And also, hardware hacking can be a little bit noisy from time to time. You're testing a building access control system, and you're swiping in every 3 seconds. It can be quite noisy. So how do we approach hardware hacking here at CyberCX? To me, hardware hacking, it's all about having the right tools and experience to fully exercise the hardware level attack surface. So recently I watched Joe Fitzpatrick, who, for those that don't know, he's a well-known, well-respected hardware hacker from the US. He made the same point at a presentation. He said, hardware is often the means to finding vulnerabilities in software. So there are also situations where hardware resilience is critical. So, for example, where you store sensitive information such as keys or intellectual property. For example, you might have a device that controls a PLC that does some commercially sensitive things, and if someone were to dump the flash that has the program on it, that could be, and reverse engineer that could be really bad for business. And also, here at CyberCX, we try to make hardware hacking a bit more accessible. So we put time and effort into research projects, trying different things. And I'll show you some of this a little bit later in the presentation. So in terms of scoping and the complexity of hardware engagements, we've tried to broadly split these into 3 levels. So the first level here is what I call limited access attacks. So this is where your adversary has sort of limited access to kind of mess with the hardware of your device. Maybe they might plug a USB stick into a USB port in the front of us, but it's unlikely they're going to grab a screwdriver and really mess with the components of it. So in this kind of engagement, we're most likely just exercise the external attack surface of the device, maybe try and gain privileged access through USB or other methods. So public kiosks or devices that are in quite physically secure buildings where it's unlikely members of the public can mess with them, for example, would probably fall into this kind of category of engagement. The second level up is what I call common attacks. So this is where we're really starting to get into the actual hardware hacking space. And this is where your adversary most likely has unlimited physical access to the device to mess with. So things like home routers, set-top boxes, power meters. Someone has unlimited time to open these apart, understand the hardware, connect to debugging interfaces, dump flash, that kind of thing. And so that's what we'd be looking at this space. So we typically open up the devices, we would connect to things like JTAG, UART, dump any flash that's accessible, maybe sniff some of the internal buses like SPI and I2C, and we'd utilize that hardware attack surface to potentially gain some privileged access. So if it's a Linux device, maybe trying to get shell access through modifying the firmware, or if it's a lower level embedded device, maybe a dump of the firmware that we can do some static reverse engineering on. So this is probably, in terms of example engagements, things like customer routers and things you're going to put in people's home premises would fit into this category. So the final and more complex engagement is what I call advanced attacks. So these are some of the really more complex but achievable hardware attacks. So devices that may fall into this category would be really important things such as building access control systems, or game consoles are a good example because they take hardware security very, very seriously. So they have things around copyright, anti-cheating mechanisms. So they put a lot of time and effort into making their hardware resilient. Anything that stores key material on the actual device, which someone has access to, and as I mentioned before, anything that stores some type of intellectual property or sort of commercially sensitive program. The attacks that we would be looking at this level 3 service would be things like fault injection, so glitch attacks, or discovering maybe side channels that allow us to recover sensitive information like key material. At this level, you'd be really thinking about your chip resiliency, potentially been looking at using chemicals to do decapsulation and mess with the wires inside the IC. A crude example of this, if you want to Google it later, is the kamikaze attack on the Xbox 360. This is where people would drill a hole into one of the ICs up to a certain point, and that allowed them to enable or disable write protection on one of the flash chips, reflash it, and they could load up games and things like that. So quite a crude example of physically modifying an IC to gain sort of extra control. And also at this level, we'd be looking at some of the more custom protocols or lower level devices that might require quite a lot of reverse engineering. And lastly, you might be looking at actually building custom boards or other sort of tool sets for actually conducting attacks at this level. So recently we had 6 of the CyberCX team attend Joe Fitzpatrick's applied physical attacks training. There's a picture there on the bottom left, looking happy and getting into it. That course is what I call really good foundation course for hardware hacking. It teaches you about JTAG, UART serial interfaces, modifying firmware, also dumping a spy flash as well. And the remaining 5 people are signed up for several courses from advanced security training. So they cover things like hacking RF with SDRs, conducting glitch attacks by using instrumenting FPGAs, some of the things that would fit more into that kind of level 3 advanced hardware attacks. All up, I haven't quite calculated, but all up it's about $40,000 of investment in training, equipment, things like that. So I'm just going to talk about some of the past research we've done in this space. And the first one that I want to mention is what we've done with the Apple AirTag. So about May last year, Twitter was sort of a buzz with talking about hacking the AirTag. The AirTag is Apple's first kind of cheap and IoT style device. And IoT has a bit of a stereotype of being, cheap garbage that you buy from AliExpress. But people are kind of curious, what do the big players do when they're in the IoT space, like Apple? Colin O'Flynn, he made a Twitter thread where he pulled the AirTag apart, figure out what components are on it, where everything fits, where the test beds are, did a really detailed tear down. And that first link there is a blog post that collates it all together. And then Stack Smashing, quite a well-known YouTuber, hardware hacker, he took Colin's information around the pin layouts and what components were there, and he kind of ran with it. So previously, a year previous, Limited Results had done some work into a fault glitch attack on the Nordic NRF52, which is actually the microcontroller that is used on the Apple AirTag. So Colin he did the first step, which was pull it all apart, see how it all worked. Limited Results had already done done research to go, yep, this is a vulnerable chip, and Stack Smashing is the one that really pieced it all together, nicely put together this nice video. So I highly recommend looking at his YouTube video if you're interested. So this is our setup. So we kind of missed out on the internet glory of being the first to do this, or at least publicize it. So as you can see in the photo, it's quite a simple setup. So there's the AirTag on the bottom right that's got some things wired into it. We're using Colin O'Flynn's chip whisperer to actually conduct the glitch. And we're just using an Arduino board to programmatically reset the device. So what is the purpose of glitching this device? So the AirTag stores its firmware in flash in the microcontroller. So it's not a component that you can interact directly with on the board. It's actually in the microcontroller. And the NRF52 uses a reprotection called AP Protect, which basically says if this AP Protect's enabled, you can't read the flash. If you want to write to the flash, it's fine, but you need to erase it first. So the idea is someone can't pull off the existing firmware that was written to it. And in theory, if you're the developer of the device, you've got the source code, so you have no reason to ever read the flash back. So with the AirTag, just skip through here. So here is a view of the oscilloscope actually doing the glitch. So the NRF is vulnerable a few microseconds into its boot, but we're looking at the V-core line here signal, which there's a slight decrease in voltage, and then you can see probably right in the middle there, it goes right down to ground really, really quickly. That's where the glitch is actually occurring. The thing about doing glitch attacks on hardware is it's never going to be particularly precise. Like it might be a few microseconds here or there. So it's a little bit of a shot in the dark. But also with glitch attacks, all you're trying to do is reverse that disabling of the read of the firmware. So you only need it to work once, so it's okay if it takes hundreds or thousands of attempts. So ultimately what we're trying to achieve here is we want to attach a debugger over serial wire debug. The serial wire debug is ARM's 2-pin version of JTAG. So it's designed for debugging purposes or reading flash or whatnot. So essentially you go through, you conduct the glitch, you try and attach the debugger. If it doesn't work, you reset it all, try again until it works. So another thing that we tried with the Apple AirTag, just a bit of a test, was how good are acupuncture needles for probing test pads and things on the PCB. And a friend of ours had 3D printed this rig where you put the acupuncture needles in. It's actually originally designed for sort of data recovery on a micro SD card, but initially Jamie, who was the one doing this AirTag research, she had soldered wires onto the test points and things. But we wondered, like, could you do this attack with very minimal kind of invasive changes to the AirTag, except for pulling the top off, of course. And yeah, the acupuncture needles worked really well for probing. There's a little bit more resistance, so it's a little bit more hit and miss whether or not the attack works or not. When you're doing precise things like this, you want it to be as sort of accurate as possible. But yeah, this is a good way to demonstrate that you can in fact do it with not too much, no soldering and nothing too invasive. So Jamie wrote up a blog post of her work around the AirTag, how she reproduced the glitch, and more importantly, how she improved it. So as I mentioned earlier, it can take hundreds or thousands of attempts to get a successful glitch and read the flash. But what Jamie discovered was that she could actually use our oscilloscope to trigger on that small decrease of the voltage just before where you want to glitch. So previously, what stack smashing was doing was glitching at boot of the device. So that kind of adds more variability. So Jamie used our oscilloscope has the ability to send a trigger signal when it notices a certain pattern. So by triggering on this sort of slight decrease in voltage and more precisely kind of guessing how many microseconds after that point it may be, she was able to pretty much conduct this attack every single time, or nearly every single time. So it wasn't hundreds or thousands. It was much more precise. So the other research thing I wanted to talk to you about was I had this thought about like how hard would it be to externalize flash, and specifically I'm talking about eMMC. So what we're looking at here on the picture is a USB flash drive that had an eMMC flash on it. And I've pulled the flash chip off, put it into a socket, which is that on the bottom left there, and then I'll kind of break out board into a flex cable. So my thought process here was these flash is usually a ball grid array footprint. So all the connections to the actual circuitry in the board are all under the chip. So there's nothing to kind of attach onto on the side. So if you want to read or write the flash, you have to physically remove it from the board, but with hot air or something like that. So my thoughts around the process would be you would remove the target flash, install what I call a transposer board. So it's the same shape as the original flash, but all it does is actually break out all the pins for the flash and then connect the actual target flash into a socket. That would allow you to more easily read and write the flash without having to desolder and hot air it and potentially cause issues with the target device. So originally there was a Chinese electronics company I saw tweeting essentially this process. So I emailed them and we had a very long and confusing exchange where I finally was able to explain to them I just wanted to buy a bunch of these sort of transposer boards that they had designed. And that's the picture on the left there, the green ones. I bought probably 50 from them. And Unfortunately, they didn't work too great. There seems to be an issue with some of the traces where between a couple of the data lines. And so it works in a kind of one bit mode, but anything beyond that point that needs sort of faster bandwidth, it just fails. So instead, Tim, one of the principal consultants here, we essentially kind of stole the design, I guess, of the original transpose board and redid it ourselves. And that's those kind of dark black, dark grey coloured boards you see on the right there. So it's essentially the same design, but there's no issues with those two the traces with the two data lines. And so, they do work. You can install them on a board. You can break out the pins into a socket. But to be honest, the whole process is still quite prone to faults, lots to troubleshoot. So this kind of idea of making it easier and more accessible, it didn't sort of pan out, but it was a good project to look at. And the last sort of piece of research I want to talk to you about was reballing BGA. So I briefly mentioned ball grid array footprints earlier with the eMMC flash. So we've tried various solutions for how to reball BGA, and when would you need to reball BGA? So if you remove a flash chip with some hot air, typically the pads under the chip get all kind of different heights or whatnot. And so if you want to reinstate the chip back onto the original board, you kind of need to tidy it up, smooth everything out, and then reball all the pads. This can be a bit of a pain. So initially we were using a stencil and some solder paste, but we found that resulted in quite a lot of bridges between the pads, because solder paste is just solder particles mixed in with some flux. So you kind of smear it over like you might do putty if you're fixing a hole in the wall or something like that. But instead, I bought a bunch of solder balls from AliExpress. That's that picture on the top left there, of various sizing, and this sort of mounting thing on the bottom left there. So the idea is you put the chip down, and then you put the stencil on top, and then you just kind of shake the solder balls in. They go through the holes, and then you get the kind of correct amount of solder on each pad. So there's less risk of bridges between pads, things like that. So I would say this is a kind of much cleaner process, and would be how I'd recommend reballing BGA. So next, hopefully halfway mid-year, I should be doing this presentation at QuiCon. So I call it hardware hacking without breaking stuff. And fundamentally, what I want to do with this presentation is show that you can do hardware hacking using tools that are less invasive. So you don't necessarily have to solder everything. You don't necessarily have to use hot air for everything, because I feel that hardware hacking has a bit of a stigma of it's sort of, you need to know lots about electronics, or you need to be really confident with soldering or things like that. But actually, a lot of tools have come along that actually make it a lot more accessible. For example, the PCB Byte, something good to Google later, is essentially an arm with a probe on the end of it, with a pogo pin on the end of it for probing. So where you might have otherwise soldered magnet wire onto test points, instead you can just probe it with these pogo pin arms. So much cleaner, less likely to cause damage. So I'm going to give you a little bit of a sneak peek into what I'll be hacking in this talk. So some people may recognize the internet box from the IT crowd. So it's essentially a flashing LED on the top of it. But Tim, again, has designed this board on the right here. It's a schematic for it, which we're calling the internet. And what this board is, essentially, it's what we often see with hardware devices. So it's a pretty simple microcontroller, it's got some JTAG, serial wire, and UART pins exposed to test points. It's got a USB. It's got one trick that we often see with manufacturers is that they'll remove simple components, for example, a resistor from a trace. Easy to easy to reinstate or get around, but that's sort of a way of disabling interfaces and things like that. So I think what I'm probably going to do is sit down and maybe make like a fake password or something to bypass, just to show that you've got JTAG access to it, you can debug it, you can recover passwords or whatever, something along those lines. And just as a side note, because I'm not an embedded developer, I don't spend time actually building things, because building things is actually hard, and especially building secure things is really hard. So maximum respect to people that actually build embedded products. But I sat down and realized just how far the sort of tool chains and things have come for embedded devices. So for example, Platform IO for Visual Studio, it just deals with all that kind of tool chain stuff that you might otherwise have had to do manually, or kind of proprietary things for the particular vendor. And you can sort of fast mode get into making your program. And I think a lot of this comes from a big push for making IoT devices an accessible thing to make. So really impressed with how the tooling is coming. Another thing just as we kind of head towards a wrap up, is I want to mention Joe Grand's hardware hacking of a crypto wallet. So some people may have seen this, but it's a fantastic example of how hardware hacking can be practical and very impactful. So spoiler alert, but Joe was able to actually get access to this crypto wallet and was able to recover about $2 million in crypto assets as a result of his work. But if you're interested in it, I highly recommend watching his video. It's not highly technical, so don't worry about that. It's more of the hacking journey, which I think is, it can be a really interesting watch. So lastly, what I want to do is to share with you some of the what I call cursed things that we've done with hardware over the last few years. So the first one here is this USB stick. So this USB stick had what's called a glop top, which is where the actual flash circuitry is just kind of all mixed in with this kind of hard solid glop stuff. So it's not a removable chip. The idea is that kind of stops you doing chipping off and reading the flash directly. But there was a bunch of pads just along the side, so I've just soldered a header along the side. This one here I wanted to show you. It's a BeagleBone Black that we again soldered a bunch of magnet wire onto points. We've essentially repurposed the SD card slot to read an eMMC flash through there. It was a bit finicky to get going, but with eMMC, often you have these partitions that are not normally accessible. So the boot partitions, boot 0 and boot 1, your bootloader might live on there if all your firmware and whatnot gets pulled off this one flash. So in order to read the boot partition, we needed to kind of read the raw flash, and to do this it would prove to be the easiest way. So on the left there on the picture is just a socket for the flash chip. Now, I mentioned the PCB byte earlier, which is some arms that have pogo pins on the bottom of it for probing purposes. But I want to show you this just because, I feel like we're sort of thought leaders in product design. So this is essentially a PCB byte, but just the homebrew really bad version of it, which is, attach a bunch of pogo pins to some cables and hold it in place. And lastly, this photo just kind of made me laugh. This was before doing a presentation on router hacking. I just kind of cut some holes in some routers and threw some wires out to the serial UART connections. Yeah, so thanks for listening to me talk about hardware hacking. I hope you enjoyed it. I really encourage you to think about the devices you're building, the devices from third-party vendors that you have on your network or use, and just, is there some situations where we could provide you with some security assurance around these kind of black boxes? And as I mentioned earlier in the slides, email or LinkedIn, I'm always happy to nerd out around hardware things. Yeah, happy to move into a Q&A.
Hey, thanks heaps, man. Look, and thanks for your time. I know that I keep saying I learn something new every time I hear you talk, and um, probably not the highest bar for this, but super interesting part of our, I guess, overall security capability that's probably reasonably unique. Um, I guess just in terms of the team, if you have any questions, please throw them out. We'll certainly stay on the line for the next few minutes. Other than that, I don't know. While we're waiting for questions, Ben, is there anything that when you're thinking about some of the recent work that you've done, are there any examples that pop to mind in terms of, I guess, interesting exploits that came out, or perhaps lessons from things that perhaps people didn't think of when deploying different hardware solutions from different vendors? Obviously, I'm not asking you to name vendors or customers, but if there's any anecdotes or stories you can share in the meantime, will be appreciated.
Yeah, well, going back to the router hacking side of things, so probably one of my favorite ways that I was able to gain shell access to a router was meta character injection through the USB name. So if you look back at some of my previous presentations, they'll go into a little bit more detail, but essentially my thought process was, what is the attack surface of a consumer router? Maybe it's the web interface or some other network services they have listening, but and often those get fuzzed to death. The ping command doesn't get passed directly into a thing, so that's all fixed. But my thought process was, well, what about plugging in a USB stick? Often consumer routers have the ability to share files of a USB stick. So this one particular router, I think it was a Technicolor router, what it was doing was it was taking the USB maker model, using that to kind of build where on the file system it's going to mount, and it passes that straight to a shell script. So what I did was use some tooling to reflash on the actual controller on the flash drive to rename SanDisk or whatever it was to kind of backtick, very short shell command. And then when you plug that into the router, you execute shell. But it was very limited in terms of characters. I think the USB model name is somewhere around 20 characters, and it would fail if there was a space. So for those that know, often $IFS in Linux can be used as a sort of space replacement, but that's sort of 6 or so very valuable characters when you don't have many characters. So fun stuff like that, like changing USB drives to wacky names to get shell access. And another one comes to mind, a similar story of firewall appliance. But it has no IP address and there's no services to attack. It just sits there, kind of layer 2 of your network, filtering packets. But there was a good example where we were able to we got shell access to the firewall after a day or so of the review. By kind of using some of the management tooling, because it does inline code management, in reverse engineering of the software, use SSH keys. But it was a good example where once we had shell access to the device, we could do a much more thorough review. You can do static reverse engineering against some of the parsing of packets and things like that. So the end result is really happy with how that review went. We were able to find some issues, and I think probably one of the craziest vulnerabilities that exploited some kind of 10-plus-year-old tar busybox issue. So these, especially in the Linux space, like it's difficult to keep things up to date, and some of these old bugs are new again.
Cool. Thanks, Ipsen. Look, there's one question that come through, and thanks, Ian. The question is, do you see keystroke loggers and other similar physical access hardware things featured in hacks these days?
They, when I think of keyloggers and things like that, I think of I've forgotten his name, but the omg.lol fella. He makes the like the lightning cables with a little computer essentially on the end of it. So not my area of expertise, because that kind of device you're probably going to be using in a, you know, some type of adversarial simulation situation where, you know, you plug a cable in that looks perfectly legit. I've not tried to build something like that before, but he would be the one I'd look. I think his website's just o.mg or something like that. So he makes some great stuff.
Awesome, man. Look, one more question, and thanks, Patrick, for the question. In terms of generic question, have there been devices you've tested or assessed that were above and beyond in difficulty to compromise?
It's a hard question to answer. Yeah.
I'll put it another way. What makes, what's the difference between a difficult, I guess, hardware compromise and perhaps less so? If that's a good question. If it's not a good question, then we call it out as well.
I think in the hardware space, especially for a security testing engagement, you're never quite sure what you're going to get. If you're working on reviewing a web application, it's pretty standard tooling methodology there. And I've said before, but in the kind of device testing space, often shell access or some type of privileged access to the device is actually stage one of the review, rather than kind of the ultimate goal. So, you're reviewing a web application, you look for issues, maybe you find some SQL injection or something like that, or some configuration, you got shell access to some web server, and that's kind of game over. Like, you've fully compromised that thing. But in the hardware space, often it's using the attack surface to get to a point where you have that access, and now you can start finding vulnerabilities. So, in that sense, if there's a minimal hardware attack surface, like it's quite a simple device, or there are things that kind of give you default resiliency, like you're being forced to have to use a fault injection issue to just even get the firmware. That can really slow down attackers for sure.
Cool. We'll take one more question, Ben. I'm not sure whether we can talk too much on this one video. Do you know of any other hacks which are similar to the Xbox 360 kamikaze hacks?
Yeah, well, that one was kind of a decapsulation without using chemicals. Maybe not similar, but yeah, I mean, that's such a blunt tool, and I think it's fantastic. But what I can do is, we're actually looking at this thread today. If I post in the chat here, I imagine everyone will see it. But there's a good thread there around. They do two things. They do a fault injection attack and also a side channel attack to recover some keys. So this is what's the microcontroller? It's the one used in the key fob for the Tesla Model 3, and it has the same kind of flash protection as the AirTag does, where you can't read the flash without erasing it. So they're able to do a fault injection to dump the flash and then do a side channel to get some keys. So not quite answering your question of like similar to the kamikaze attack, which was a physically modify the IC thing, but the Twitter thread's got some really good actual hardware level attacks in it, which I think is a great one, and it's super fresh because I think it's just come out today. And I would also recommend just keep looking at game console hardware things. There's a bunch of videos on YouTube, because Microsoft and Sony have definitely taken, and Nintendo. There was the Tegra, the NVIDIA fault injection recently in the Nintendo Switch, which is an interesting one. So I recommend Googling that, watching some videos in that space if you're interested in especially game console hacks.
Awesome. Look, thanks, Hipspan, and thanks everyone for sticking around for questions. I think my takeaway is the constant reminder, not that I need one, to think about attack surface over and above the software aspect of things, and thanks for the reminder on that. If you have any questions off the back of the session, team, feel free to reach out to, like I said, Ben over LinkedIn or via his email on the contact address. Also, we'll drop you a follow-up link with a recording to the session. Quick reminder, next week we have Vanessa Vanessa Letty, presenting on DevSecOps, aligning security to agile way of working. It's a bit of an insight into some of the, I guess, our thinking around how to think about security when it comes to your CI/CD pipeline, and a little bit of detail behind that. So hopefully we'll get a chance to see you then. Otherwise, thanks again for your time. Hope it was valuable and enjoyable. Look forward to any feedback that you have in the session as well. Thank you and enjoy what's left of your day. Thanks again, Ben. Thank you.
Thanks, everyone. Cheers.